All right, everyone, let's go ahead and get started. I want to kick off today's explainer by asking you a question that honestly seems so simple a toddler could ask it. Yet it actually unlocks one of the most profound mysteries in all of physics. Why do things actually fall towards the Earth? Seriously, take a second to really think about that. When you drop your pen, why doesn't it just hover there? Or, fall upwards? This foundational mystery is exactly what we're going to dive into today.
So welcome to Physics 101. I'm absolutely thrilled to have you here. Today, we're acting as scientific detectives, unlocking the universal law of gravitation. Consider this your digital chalkboard session, where we're going to demystify one of the absolute most important invisible forces shaping our entire universe. Grab your notebooks, because we are breaking down the mechanics of the cosmos step by step.
Here is a quick look at our syllabus for today's explainer. We'll start with the falling mystery, then introduce the universal law of gravitation. After that, we'll build the gravity equation itself, followed by a mind-bending look at equal and opposite forces. Then we'll crunch some real-world numbers in calculating human gravity. And finally, wrap up with the inverse square law.
Okay, let's jump right into Chapter 1, the falling mystery. Returning to that opening question, what actually happens when you lift an object up above the Earth's surface and just let it go? Well, instantly, that object accelerates downward, straight towards the center of the Earth. In physics, we explain this very specifically. The object, at that particular height, is experiencing a downward force. It is literally being pulled. And due to this unseen force, it falls. We call this downward pull of the Earth on an object gravitational force.
Now, this presents a rather profound paradox to us as physicists. You're probably wondering, okay, but why does this downward force even exist? What is the actual origin of it? Well, class, the incredibly humbling answer is, we don't know. No scientist in physics can actually explain the true origin of gravitational force. Just like magnetic or electric forces, where it comes from is a total mystery. But, and this is a massive but, while we can't explain its origin, we have incredibly powerful laws that let us calculate this force with astonishing precision.
And that brings us to Chapter 2, the universal law of gravitation.
If we can calculate gravity so perfectly, who gave us the tools to do it? Well, many brilliant minds chipped in over the centuries, but Sir Isaac Newton is the absolute genius who gave us the definitive law. The universal law of gravitation states that there is a gravitational force, an attractive force, between any two masses. I really want to emphasize that word any. It does not matter if the two masses are living bodies like you and me, or non-living bodies like two rocks in space. Literally everything is pulling on everything else.
All right, moving right along to Chapter 3, building the gravity equation.
So how did Newton actually quantify this universal attraction? Let's visualize two objects. One has a large mass, let's call it capital M. The other is smaller, small m. And they're separated by a distance we'll call r. If someone asked Newton, hey, how much attractive force exists between these two things, here is how he built the answer. Step 1. He figured out the force is directly proportional to the product of the masses. Basically, multiply capital M and small m together. Step 2. The force is inversely proportional to the square of the distance between them, or r squared. And step 3, to turn these proportional relationships into a concrete, usable mathematical equation, he had to add a constant, known as the gravitational constant, or capital G. And when you put all that together, you get this brilliantly beautiful final equation. Force equals G times the product of capital M and small m divided by r squared. This one single line of math gives us the gravitational force between any two masses in the entire universe. Oh, and that capital G, it's a very specific constant value equal to 6.67 times 10 to the power of negative 11.
Which leads perfectly into Chapter 4, equal and opposite forces.
We're going to take what we just learned and combine it with another one of Newton's famous concepts to really challenge your intuition here. Remember Newton's third law of motion? For every action, there's an equal and opposite reaction. So if you hold a 1 kilogram object above the ground, the Earth exerts roughly 10 newtons of force on it, pulling it down. But check this out. According to the laws of physics, at that exact same moment, that tiny 1 kilogram object is also exerting 10 newtons of force pulling up on the Earth. The forces are perfectly equal in magnitude. The Earth pulling on the moon pulls back with the exact same force.
So I know what you're thinking. If a falling apple is pulling on the Earth with the exact same force that the Earth is pulling on the apple, why doesn't the Earth fly upwards to meet it? The answer is just one word: Mass. The mass of the Earth is tremendously, unimaginably larger than that tiny apple. Because of this colossal difference in inertia, the Earth doesn't even flinch, it doesn't accelerate. Instead, the smaller object does all the moving.
Let's put this into practice. Chapter 5, Calculating Human Gravity.
Let's test this in the real world with some everyday numbers. Imagine a boy and a girl standing next to each other. Capital M, the mass of the boy, is 40 kilograms. Small m, the mass of the girl, is 45 kilograms. The distance between them, our r value, is half a meter, so 0.5 meters. And we'll plug in our constant, g, which is always 6.67 times 10 to the negative 11th. We want to find the gravitational force between them, so we just plug it all into Newton's formula. Multiply the constant by 40 times 45, and then divide that whole shebang by 0.5 squared.
And when you run those numbers, the gravitational force between this boy and girl is exactly 4.8 times 10 to the power of negative 7 newtons.
Let's just appreciate what that number actually means. 4.8 times 10 to the negative 7 newtons is a microscopic, unimaginably small force. And the math works perfectly to describe our lived reality here. Yes, these two people are physically pulling on one another with the force of gravity, just like planets do. But because human masses are so incredibly tiny compared to celestial bodies, the force is virtually zero. That's exactly why you don't feel physically pulled into the person standing next to you on the subway.
Finally, we've arrived at our last chapter for today, the inverse square law.
Consider this a bonus round for my overachievers out there. We established that gravity is inversely proportional to the square of the distance between objects. But what does that actually mean in plain English? It means if the distance between any two things doubles, increases by 2 times, the gravitational force doesn't just cut in half, it decreases by 4 times. If the distance triples, the force decreases by 9 times. Because distance is squared in the denominator, gravity fades out incredibly fast as objects move apart. That's why we call it an inverse square force.
As we wrap up today's explainer, I want to leave you with one final mind-expanding thought experiment. If distance exponentially shrinks gravity according to this inverse square law we just discussed, is there anywhere in the universe, no matter how vast or how empty, where your personal gravitational pull on the cosmos is mathematically zero? Think about the equation we just built and what it implies for everything in existence. Thank you all so much for joining me today. I really hope this sparked your curiosity to learn even more about the incredible forces holding our universe together. Class dismissed.